All right, welcome back everybody. In this video we're going to be discussing material from Unit 1, Section 13 of AP Calculus, removing discontinuities. There's not really a whole lot of new information in this particular lesson. We're just going to go through a bunch of examples that show us how we can remove discontinuities from functions and the necessary information in order to do so. All right. Let's go ahead and we're going to start here with example 1. It is known that for the function f of x given below, that the limit as x approaches 4 of f of x exists, and that f of x is continuous on the interval from negative infinity to infinity. And we're supposed to find the value of k. Okay, so in order to find the value of k, we know that this function is continuous. And if I look at the individual branches, I have this top branch that is a quadratic, and we know that all quadratics are always continuous from negative infinity to infinity. I also have this bottom branch, which is linear, so it's a polynomial, again, and we know that all polynomials are continuous. So each of these branches individually of themselves are continuous. So what we need to do in order to show that, or in order to find this value of k, is we need to show that it is continuous where these two branches meet at x equals 4. Okay, so we could kind of go through the 3-step test here for continuity. We could first find f of 4. Okay, and f of 4 we're going to get from this branch, since that's the one that has the 4 included in its definition. So we can go ahead and substitute 4 right in there. And we find that f of 4 is equal to 6. Okay, then what we need to do is we need to show that the limit exists, and what value of k we can find that the limit exists as x approaches 4. So we're looking for the limit as x approaches 4 from the left to be equal to the limit as x approaches 4 from the right. I'm just kind of splashing information about what we need to know here. So the limit as x approaches 4 from the left of f of x is, sorry, got a little bit ahead of myself there, writing-wise. Well, which of these branches is the one where x is coming to 4 from the left? It's where x is less than 4. So it's this branch, the x squared minus k branch of the curve. And the limit as x approaches 4 from the right is going to be the other branch, negative 3x plus 18. Alright, so now I'm going to find both of these limits via substitution. I can just substitute 4 in to find the individual limit for each branch, and if I do that for the left branch, it gives me 16 minus k. And for the right branch, I know if I substitute 4 in there, I'm going to get 6. And then we can just go ahead and solve this equation for k. And that's the value of k that we want in order to guarantee that this function is continuous on the interval from negative infinity to infinity. All right, let's go down to example 2. Find a value of a that makes the following function continuous. Again, one of these is going to give us the function value at x equals 2. 2 is where we're really concerned. Again, we talked about it a little bit with the first example, but both of these branches of this piecewise function are polynomials, so they are continuous everywhere where they're defined, everywhere on their domain. And so we know that the function is continuous everywhere except for x equals 2 right now. And whether it's going to be continuous at x equals 2 or not is going to be determined by the value of a. Okay. So what I'm going to do, again, I'm going to set up, kind of like I did last time, I'm going to set up the limit as x approaches 2 from the left of this function has to be equal to the limit as x approaches 2 from the right of this function. And as x approaches 2 from the left, we're using the top branch of the piecewise function, since that's the values to the left of 2. I did it again, just copied my f of x in there. So there we want to find the limit of ax squared minus 2. And for the other branch, we want to find the limit of 3x minus 5. And something that you want to, take note of here, since I'm kind of, dancing around the test for continuity, what we know in this function is that the limit as x approaches 2 of this branch is going to be the same as f of 2. And so we're really taking out two pieces of the test for continuity. We're finding the value of f of x at x equals 2, and we're finding the limit as x approaches 2 of that one side. And we just need to match that side up with the other side in order to guarantee that this is continuous. Alright, so now I'm going to go about substituting 2 in here. And if I substitute 2 into the left branch for x, it gives me 4a minus 2. And if I substitute 2 into the right branch, it gives me 6 minus 5 is 1. And from there, some pretty simple algebra. And we get that a value of a equals 3/4 is going to make this function continuous. All right. I guess I could really talk quickly about this piecewise function and the graph of it. We're talking about, let's see, f of x for x less than 2, f of x equals, and I need my braces. For x is less than 2, right? Yeah. X is less than 2. We're going to have ax squared minus 2, and we said that a was 3/4. 3/4 x squared minus 2. And for x greater than or equal to 2, this was 3x minus 5. Oops, 3x minus 5. And so you see what this piecewise function looks like now when a is equal to 3/4. Now, if I change the value of a here, suppose I made a 2 instead, you see how the two branches of the piecewise function don't connect. Any other value of a that I put in here, the two pieces do not connect. And so just a little bit of graphical explanation, graphical support for that being our value for a. All right. One more example here. Example 3. Give a formula for the extended function that is continuous at the given point, and sometimes we refer to these as continuous extensions. In other words, what's going on with this function? When we see this, f of x equals x cubed minus 1 over x squared minus 1, and when we say at this given point, at x equals 1, what I'm telling you by writing it this way is that there is a discontinuity in this function at x equals 1. And you can see that very easily if you substitute 1 in, like you're trying to take the limit of this function, you end up with an indeterminate form 0 over 0. And so when we're trying to find an extended function that's continuous, what we're trying to do is, what we've got here is a removable discontinuity. And we're trying to fill in the hole. So in order to fill in that hole, what we're going to do is we need to find what value the limit has as x approaches 1, because then we're going to define that as the value of the function, and that'll turn this into a function that fills in the hole. Okay, so for instance, let me show you real quick. I'll use my graphing calculator. If we put this in here, y equals x cubed minus 1 over x squared minus 1. If we graph that in a standard window, okay. At x equals 1, the function is not continuous, and that's not necessarily obvious when you look at it, but if you trace this graph and you type in 1, you see that there's no y coordinate there when we trace this graph. And so the graph has a removable discontinuity at x equals 1, and we are trying to figure out the value that we can fill that hole in with. Okay, so first thing I'm going to do, I try to find the limit as x approaches 1 of x cubed minus 1 over x squared minus 1. That leads me to a 0 over 0 indeterminate form. And so I am going to factor. Factoring the numerator, or the denominator, is easy enough. Factoring the numerator is a little harder. I know x minus 1 is a factor, and if I know my difference of cubes factoring pattern, this one's not so difficult, which thankfully I do. And then we're going to go ahead and cancel out the common factors. And so this is going to be equal to the limit as x goes to 1 of x squared plus x plus 1 over x plus 1. If we substitute 1 in here for x everywhere, we get 3 halves. And so we can write a continuous extension for this function by saying, okay, here's my continuous extension g of x. It's going to be the original function f of x everywhere where x does not equal 1. But where x equals 1, I need this value to be 3 halves. And that's going to fill in the hole. And so that's a good way for us to write a continuous extension. Say that it's equal to the original function everywhere except for at that point of discontinuity. And then it's this numerical value at the discontinuity. Now, I personally have what I like to refer to as my sneaky answer. There's another way to write this particular continuous extension. And remember back here where we canceled out the common factor and then this was what was left? That means that these two functions are the same, look like the same function, except this one fills in the hole that existed in the original. And so another way to write this continuous extension for this one is like so. Alright, that's where we're going to call it quits for this video. We'll be back with a second video on this topic where we're going to go over examples 4 through 6 from this lesson. Alright, see you next time. Have a great rest of your day.